So just to let you know, we're recording today's session. It will be available on the Teams channel after the session, and we will also share any available slides. So if you've missed it, you can catch up later. In a few weeks or so, Rachel's going to be having a bit of a look back to review all of the topics we've covered since we started the huddles and pulling together some ideas for the future. So do, when we get to that, please do contribute and help us to shape what we do going forward. We'll finish at 12 o'clock or just before. If you've got any questions or comments, use the chat box or just shout out. And if you can't use the chat box, we'll leave Menti open to pick up any questions for Joe and Santosh. Please keep yourself on mute unless you want to say anything at any point or ask a question. Raise your hand if you can, but otherwise do just shout out. And as usual, these sessions are for you, and we like to keep them as informal, but hopefully as informative as possible. So before we kick off, we're just going to pop over to Menti. So I'm going to share my screen. Has that come through? If you go to www.menti.com and use the code 13195546. I've popped that in the chat, but once you're in, if you could press the thumbs up or the cat or the heart, that would be great. So that's brilliant. So in true huddle fashion, I've started off with a completely random, unrelated question. Are you doing a January challenge? If so, which one are you doing? Oops. My favourite is getting out of bed in the morning so far. So we've got a few dry Januaries, we've got a few no's, we've got more no's, we've got a 10-minute headstand. Is that a 10-minute headstand in January or a 10-minute headstand every day in January? And that's awesome. I'm going to take my hat off to your skills. We've got a daily run in there. I'm doing run every day in January, and that's painful. Exercising every day, COVID recovery, not this year, getting through each day. So thank you for taking part. That's great. And I know it's a bit random, but just going to scan through. If you've got any questions for Joe or Santosh or comments in general, could you please put them in here, and we'll leave this open for the duration of the session. Also, do just pop anything that you've got into the chat. And without any further waiting around, I'm going to stop sharing my screen and hand over to Joe and Santosh and let them pick up and talk to us about machine learning. Thank you.
Yeah, thank you. And thanks all of you to joining this session. And I'm Santosh Kumar. I'm a data scientist at HU, Health Economic Unit at MLCSU. And on the other hand is my colleague, Joe. Joe, you can introduce yourself.
Hello, everyone. Thank you for coming today. So I'm a data scientist in the Health Economics Unit and my background's in machine learning, so and in sort of physics engineering and general analytics.
Yeah, great. So
So
yeah, so somehow our camera is not working due to this link. So anyways, yeah. So share my slides. So during this talk, we are going to present machine learning and its application. I hope you all can hear me, right?
yes.
Okay, yeah. So yeah, during this talk, we are going to discuss about an overview of what is machine learning, which is I'm gonna present here, and then my colleague Joe, he's gonna present like about what are the possible application in healthcare and in general for this machine learning application. So let's see. So these days the world is filled with the data, and the data is about a lot of data related to the picture. In healthcare, we can say the MRI and CT images, music, videos, text, spare sheets, and it does not look like it is going to slow down any soon. So the machine learning is brings the promise to driving the meaningful from that data. So probably you guys heard a lot about many application in machine learning, definition about the machine learning. So I have shortened this definition in machine learning, and I can sum up like within just 5 words. So what is machine learning? Machine learning is using data to answer the questions. Then we can split this definition into the 2 parts. The first part is using the data and and the second part is answer the questions. So these 2 pieces like broadly outline the 2 sides of machine learning, and both of them are equally important. For example, using the data, we refer to here training our model, and while answering the question is referred to as a making prediction or inference. So now let's drill into these 2 sides briefly for a little bit. So these is like a traditional machine learning pipeline where you has like data processing step, and then you have to do your training your model, and you have to do the modeling and then testing and there's predictions. So training refer to using our data to inform the creation and the fine tuning the predictive model. So this predictive model can we then serve up the prediction on the previously unseen data and answer those questions as more data is gathered. So the model can be improved over the time, and a new prediction model can be deployed. So this is a continuous learning cycle. So whenever you collect the more data, you have to retrain your model, and the more data you will collect, the more you will retrain, the better your prediction model will be. So there are the many types of the machine learning, but broadly we can divide into the supervised machine learning, unsupervised machine learning, and the reinforcement machine learning. So in supervised machine learning, the goal is to generate the formula based on the input and the output values, and the unsupervised machine learning, we find an association between input values and then we group them. In reinforcement learning, we have an agent learn through delayed feedback by interacting with the environment. So these are the broadly 3 types of the machine learning, but we can further subdivide into their classifications. But it's all depends on the problem what you are going to solve and what kind of the data you have. So probably you heard about many like application about the machine learning, and you wonder, well, how exactly those work. So let's have in here basic example where we can understand like how the machine learning exactly work. So let's have this example where we have been asked to create a system that answer a question whether a drink is wine or beer. So this question answering system, we are going to build a system or a process is called model, and this model will be created by a process is called training, and the goal of this training is to create an accurate model that answer our question correctly most of the time, but not in order to train a model. We need to collect a data to train this model. And which can then, once you created this training model and you train very well, then it will be ready for the predictions. So the very first step for all this process is, as I said, we need to collect the data. So our data will be collected from the glasses of wine and beer, and there are many aspects of the drinks that we could collect the data on. So everything from the amount of the form or the shape of the glasses, we can collect the data. But for our purpose, we will here pick two simple variables, or you can say, or the data types from our wines or the beer glasses. So the first one is the color as a wavelength of light, and the second one is like the alcohol percentage. So the hope is to we can split our two types of drink along these two factors alone, and we can call them as a features, and so these are the two features which we can get as a color and the alcohol. So the first step to our process will be to go to some local grocery store and buy a bunch of different kind of beer and wine bottle, and then we can get some equipment to measure like the alcohol percentage and the color of the beer or the wine. So for the color we need an equipment is called the spectrometer, which can measure the color, and for the alcohol content probably we need like the hydrometer, which can measure the content of the alcohol. And then once we got this equipment and our booths are ready to set up, then it's time for our real setup for the machine learning algorithm, which is like data gathering. So this step is very important because the quality and the quantity of data that you gather will directly determine basically like how good your predictive model can be. So in this, the data we will be collect is like related to our two features. One is the color, and the other one is the content of alcohol content of each drink. So this will provide a table for color and the alcohol percentage and whether it's a beer and wine. So this is the process like where our data preparation is done. So like after a few hours of measuring these alcohol and the color data, so here is like the next step we have to do. We have to visualize our data, whether for example our data is correct or not. So this is a time we can verify the data preparation or the data gathering step. So sometime what happened, like sometime you get like more wine bottle in comparison to beer bottle, so you collected like more beer data rather than the wine data. So this problem is called the data unbalance problem. As you can see here, the beer content, the beer data is more than in comparison to wine data. So yeah, so then we will first put up all data together and then randomize this data here in randomized data in ordering. So we don't want that our data will be affect of the learning in particular outcome. So that's why we created a randomization of this data. And Then once you gather this data, we need to split the data into the two parts. So the first part is used to training our model, will be the majority of our data, and the second part will be the evaluating of our model's performance, which is the evaluation data. And we don't want to use to the same data for the model which was trained for use the evaluation. Yeah, so sometimes the data we collected need the other format. For example, we need a data manipulation like duplication, normalization, error correction, and the other step. But luckily, we don't have to do any perform any those steps here. And then our next step in our workflow is to choose a model. So there are many models that researcher and data scientists have created over the year. Some are very well suited for example, image kind of data. Other are for the sequences, and sequences such as, for example, text, music, numeric data, and a few other are for the text-based data. So in our case, we just have, for example, just two features. One, as I said, feature as a color, and other one is a feature as an alcohol percentage. So we can use a very small linear model, which can fairly simple one, and that can do the job. So now we move on what is often considered. So now we move on what is often considered is a bulk of machine learning, the training. In this step, we will use our data to incrementally improve our model ability to predict whether a given drink is a wine or beer. So in some way, this is the training process is very similar to someone who first learned to drive. At the first, they don't know how to operate, for example, the pedal, knobs, or the switches in the car, and when they should press the brake, and when they should release the brake. However, after, so this is like a first time learning, but eventually when we get like the experience of, we get like licensed as a licensed driver emerge, the more after years of driving, we became like quite adaptive to driving, and we get drive very well. So it's the same thing happen in the machine learning. When you first train your model, might be your model is not producing that much good outcome or the accuracy in terms of the metrics. But for example, when you go through the number of iteration to do the modeling or to do the training, then our model became much more better and produce the better outcome. So in our case, we will do this on a much smaller scale with our drinks. In particular, the formula for a straight line is y equal to mx plus v, where x is the input and y is the slope of the line, and the v is the y-intercept, and y is the value of the line of that position. So the value we have available us to adjust or the train are just m and b. We can't do anything about the y. So where m is the slope and b is the y-intercept. So there is no other way to affect the position of a line, since the only other variable is x and our input y and input and our output. So in machine learning, there are many why, since there are maybe many features. The collection of these value is usually informed into the matrix. That is denoted by the W and for the weight matrix, and similarly for B for the biases, and we arrange them together, and this is called the biases. And then the training process involve the initialize some random values of W and V and attempt to predict the output for those values. As you might imagine that it is a pretty poorly first, but it can compare it. I mean, we can compare our model's prediction with the output that should be produced and adjusted the value of W and V such that we have more accurate prediction in next time around. So this process, as I said, is as a repetition of cycles for updating our weights and the biases. And this particular process is called the training steps. So let's look. So let's look at what means more concurrently for our data set. First, we start the training, and it is like draw a random line through a data. As you can say here, we have like two kinds of features. The first one is the related to the color, and the other one is related to the alcohol percentage. And our goal is to draw a line which can perfectly divide like these two classes. So at the very first, when we start as a very initial stage of training, our model is just randomly draw one line to separate these two classes. And at the very first line, this you can say it's not a perfect classification, or you can say it's not the perfect division, but along with the time when you iterate your process of modeling, our model is getting much more intelligence, and it is creating a better decision to dividing these features. So after like getting like the number of iteration, our model is working very well. So once you are satisfied with your model training, that in the training time your model is doing this kind of perfectly division, in reality you should never get this straight line. There's always trade-off between how many outlier you are allowing. For example, how many data points belongs to the alcohol contents you are allowing into the data points into the alcohol color, and the vice versa. So once you are satisfied with your training, the next process is to evaluation of your model. So this is where the data that we set aside earlier comes to play now, and the evaluation allow us to test our model against the data that has never been used for the training. So this metric us to see how the model might perform when we throw the data which is completely unseen, and this meant to be like representative is how the model is basically might perform into the real world. So yeah, and after that, so often like people have like question, what is the thumb rule to dividing this training and the evaluation part? And then I should say, when you have a smaller data set, then always try to split into like 80 to 70% ratio for the training and 20 to 30% for the evaluation. And if you have very large data set, then might be you can go through 60 to 70% for the training, and 30 to 20% for your evaluation of training data. So once the evaluation part is done, it is possible that you want to see if you can further improve your training in any way. So we can do this by tuning some our parameter, and there were a few that the parameter we implicitly assume that we have did our training, and now it is good time to go back and test those assumptions and try different value for the hyperparameters. And these parameters is basically called the hyperparameters. And another parameter is like the learning rate. So this define how far we shift the line during each of the steps. So for example, here we are shifting the line at the every iteration. So this is called the learning rate parameter. So these value all play in a role that how accurate a model can become and how long the training will take. For more complex model, initial condition can play a significant role, as well as you can determine the outcome of training. So the difference can be seen depending on whether a model start off training with the initialize of 0 versus some distribution of value, and that can determine like what are the distributions here. So once you are done with your training and you are happy with your, for example, training and hyperparameters tuning, and then the next step is to check the predictions for your model, whether the given drink is as a wine, and the given drink is a wine or it's a beer. So we can finally use our model, as I said, to predict like whether this is wine or the beer. So the power of machine learning is that we were unable to we are able to determine how the differentiate between the wine and beer using our model rather than just human judgment, and then maybe some by the manual rule. So you can extrapolate this idea presented today with other program and in other domain as well, where the same principle apply. For example, the steps which I mentioned as a data gathering, data preparation, choosing a model, training and evaluation, and doing the hyperparameter training, and then finally the prediction. So from here, my colleague is gonna give you some idea how we can apply this machine learning step, which I mentioned, to some very general and also the healthcare related domain. So Joe, it's all your now.
Thanks, Santosh. Shall I do the slides? I think that's easier.
Sure. Yeah.
Okay, so I'm going to be talking about the various applications of machine learning in healthcare.
Sorry to interrupt, Joe. Before you move on,
yeah,
there's a couple of questions in the Menti, and there's one that I just wanted to ask Santosh. Are weights and biases just trying to find the slope and y-intercept? And what is the difference between finding the correct weights/biases and parameter tuning?
Yeah, so there's always like a trade-off, as I said, like the trade-off between how many like outliers you are allowing into your machine learning. So the calculating the correct bias and weight is depend on the trade-off of that trade-off value. So for example, if you are saying like, okay, the 10% I have a 10% trade-off value here, it means you are allowing the outliers from one class to another 10% data points you are free to move there. So this is how we determine like which is the best slope for to dividing these two classes.
Thanks, Santosh. There's another question about slides, but we'll put that up at the end. Sorry, Joe, I'll hand it back to you.
That's fine. Okay. Yeah, so as I was saying, my presentation will be talking about the various applications of machine learning in healthcare, and I'll try and illustrate them through various examples, which are a lot of different papers across the literature, and I provided the links and you can look in your own time for more detail. Sorry, my slides aren't working.
Do you want me to go through it?
I'll try and share them again. Okay. So in the HEU, which is what Santosh and I are part of, we're involved in several different projects, which to varying degrees can or have used machine learning. So Santosh has been involved in a big machine learning study predicting heart failure We've also done work on linking the length of stay in a hospital to future readmission. And also we're getting involved in a project that looks at predicting hospital admission for what's called ambulatory care sensitive conditions. These are conditions in which an intervention in the primary care can potentially reduce the probability of admission to hospital. Okay, so there are numerous applications of machine learning in healthcare, and these can do, in terms of predictive analytics, these can predict on different granularity. So they can predict patient level outcomes. For example, does a patient have diabetes or not? Will they have a stroke or not? They could be predicting on a hospital level. So this could be looking at, can I predict which hospital goes into emergency response? Or they could, look on an even larger scale. Can I predict the health benefits of one country compared to another? Now, machine learning can link various parts of the healthcare system. So you can link primary care to secondary care, for example. So in other words, how does the practices offered by GPs influence hospitalization in the secondary care? Or you could look at other aspects. So, for example, how does hospitalization influence future life expectancy, or how does it influence the tertiary care system? Machine learning can identify patients at risk, but it can also be useful in determining associated factors which are potentially interventional in patient care. And as well as for predictive analytics, machine learning can be used for better understanding your data. So, for example, it can be used in clustering groups of patients with similar health conditions. So there are broad applications across both the public and private sectors. And I've put a list here. These are just, some of the thousands of different areas machine learning could be applied to and is. So, for example, in imaging, in emergency care, could be in traumatic brain injury or various diseases such as leukemia or dementia. So I just put, one example paper here, and I've got the link at the bottom right. Machine learning, can be used for decision making. And so in this study, what they were trying to do was they were combining different MRI modalities together in order to differentiate whether or not a patient has Parkinson's disease or whether they have progressive supranuclear palsy. Now, typically, a radiographer would look at each of these MR scans separately, but this would be an all-encompassing, one way of combining all of the different MR scans in one single model. Machine learning can also be used in real time. So it can be, there have been papers published where machine learning has been used to develop an early warning system for circulatory failure in emergency care. And so what the system is trying to do here is it's trying to combine various measurements from different organ systems together in order to give you some machine learning output, and depending on the output, that can trigger the early warning system. But machine learning can also be used in various other things. So it can be used in mental health. So the paper here, what it was trying to do was differentiate between patients with bipolar disorder and major depressive disorder. And to do this, they used a variety of different variables in the machine learning. So they took some from questions and answers from a mental health questionnaire, and some from blood biomarker information. Okay. As well as predictive analytics, machine learning can be used to determine a better mechanistic understanding of medicine. So in this study, it was an opioid addiction study, and they knew at the start of the study that opioid addiction was thought to damage the prefrontal cortex. But what they used machine learning for was to actually show that. And they did that by coupling, the machine learning was used to couple brain signals, so in the form of EEG, with some form of localization on the brain. So this is non-invasive neuroimaging. As I mentioned earlier, machine learning can be used in traumatic brain injury prediction. So here the study tried to predict 30-day mortality, but importantly in a real-time fashion during intensive care, and that's following traumatic brain injury. Sorry, slides are playing up a bit. Okay. One interesting paper I read recently was the use of machine learning in predicting mortality risk in patients pre-chemotherapy. And that's obviously important to assess because chemotherapy does come with, certain side effects, and so there should be a cost benefit, performed of whether or not chemotherapy is appropriate. And machine learning can also be used in radiotherapy. So it might be of value to use an MRI image to determine the dose in radiotherapy. And what this study was doing was it was trying to determine the dose by linking together MRI to predict what are called synthetic CT images. So these are sort of fake CT images that you establish from learning using machine learning to analyze the correlation between MRI and CT. Machine learning has also been used, across the drug discovery cycle, and that applies to all different stages, right the way from target discovery, so understanding which drugs you might try or which diseases you might target, to the actual implementation, clinical development. And once they have a drug approved, it can also be used in post-approval. So, for example, in price point matching or in assessing the at-risk patients. I think I'll do one more example and then I'll move on. Here's an example from surgery. So in surgery, the anaesthetist is concerned about hypoischemia. And here in this study, machine learning was used to basically predict the likelihood of hypoischemia in a patient. And that's obviously valuable information for the anesthesiologist, so that they can, take extra care. So there is a wide-scale use of machine learning, certainly in healthcare, but obviously there's a huge amount being done in other industries, right the way from the financial industry to manufacturing to transport. You probably name the sector, there'll be some machine learning in it. And so healthcare can learn a lot from these industries. Now I just give you a sort of example approach to machine learning in healthcare. And to do this, I've made up a project. So the example I have is, imagine that the UK trials a 4-day working week. And the machine learning question is, well, can I predict the health benefits of this? Now, on the face of it, you might think, well, there's really only benefits. A 4-day working week gives you more time to exercise, gives you more time to relax, gives you more time to get outdoors and sort of see family and friends. But at the same time, there may be actually some drawbacks that make this quite an interesting machine learning question. For example, it might be that your boss now thinks, well, you now have to fit 5 days worth of work into 4. So the 4 days that you're working are incredibly stressful and bad for your health. It might be that you're less sort of, you don't necessarily make use of the extra free day. So perhaps you spend the day lying in bed and eating takeaways, or perhaps the general services that you might want to access no longer exist to the same amount. So, for example, hospital capacity might be reduced, or the working hours of sports centres and gyms, so you can't exercise at the same times. Perhaps you'd hate the thought of having a 3-day weekend. Perhaps you might get lonely, or you might have sort of mental health issues, or there might be another factor in that there might be increased mental health issues because of financial worries, because of working 4 days and not 5. Imagine this scenario. That would be an interesting machine learning question. The first thing you would do is you would try and establish which data you might use. And for this, as Santosh explained, you need some training data and you need some test data. And now the training data, you might think, well, which countries have trialed the 4-day week? So you might look for, Iceland's data, or New Zealand, or Spain. Then you would look at, well, can I get access to that data? And data access can be a challenge in healthcare. As well as that, in terms of test data, you might say, well, I want to test out my problem on the UK population. But what data do I actually want? Do I want primary care data? Do I want secondary care data? Am I looking for an integrated data set? And then once you have your training and test data, you ask the question, well, are the 2 data sets compatible? Do you have similar coding on the health conditions? Are the variables similar names? To what extent is the missing data the same or different in both data sets? Okay. So the next step, once you have your data, is to establish which variables should I choose. Now, you can choose a number of different variables. Some might be related to demographics, for example, gender, ethnic group, age. Some might be related to occupation, for example, what job sector do you work in? Do you work from home? Are you self-employed? And then, of course, health clearly comes into the question. So what's your history of disease? Are you a smoker? Are you overweight? Are you a regular exerciser? Then, of course, you need to think about, well, which outcome is important to predict? So do I want to predict the probability of admission to hospital in 2 years? Do I want to predict someone's life expectancy? Or, for example, do I want to predict the probability of death in 10 years' time? So once you have the data and the variables, you then need to pre-process it. Now, typically, you ask the question, how do I deal with any missing data? Do you throw it away? Do you fill it in by interpolation? Also, some of your variables will be numbers, some will be categorical variables, so you need to think about encoding the variables in the same way. You might have too many variables to consider, so you might need to aggregate them or throw them away from the problem. And of course, you should try and avoid any data leakage into your training and test predictions. So once you've done that, you need to think about a model, and I would always advise choosing, choose a range of simple to more complex models, but at least initially, don't throw everything you have at the problem if it's not needed. So the simple models are easier to implement, they are easier to explain, and they have a higher chance of being used clinically. If you've decided on a model, you need to train the model, and the level of training will depend on a lot of things. So it will depend on what computational time is reasonable, particularly in terms of the project deadline. It will depend on what computational resources you have. So are you working on your own low power laptop, or are you working on a cluster with 100 cores? You might, of course, train on some subset of the data if training on the full data is not practical. Once you've trained the data, you need to evaluate it. So you might choose multiple metrics in the evaluation, and you should be aware of how a metric might be misleading or influence clinical decisions. And the type of metric will depend on the type of machine learning problem. So, for example, you might have heard of regression versus classification metrics or other ones. Once you've evaluated the model, you would then deploy it potentially. So you think about which server could I put it on, who might have access, do you want to make the code open source, or is it entirely confidential? Once the model is deployed, there's actually a lot of work that can be done in reusing the model for other applications. And I say this because I see in a lot of machine learning problems, they can often be mirrored. So for example, if you were to do a problem predicting whether or not a patient has diabetes, that in terms of a machine learning problem is quite similar to will the patient have a stroke or not? And in that sense, machine learning in healthcare can learn a lot from other industries, because often you need to think about the machine learning problem you're trying to solve first, and then that can drive how you develop the code. Okay, so I think it's sort of 10 to, and I think I'll stop there. So thank you very much for all of your attention, and I think Santosh and I would be happy to answer any questions that you might have. So thank you.
Thanks, Joe, and thanks, Santosh. That was really interesting, really useful, and I'm sure we've all got a lot out of it. There are a couple of questions in the Menti. The first one is a question about what software do you use in the Health Economics Unit for machine learning?
Sure, I can answer that. Typically, we use Python or R because they are well supported. Well, they're generally well suited for machine learning in terms of what libraries they have, but also they're well set up on many of the patient level databases that we use.
Thank you. Is your R code open source? Do you make it available for other people to share?
That's a good question. Santosh?
Yeah, not at the moment, because we have our own Git repository, which is not open source, but definitely we have future plans after delivering successfully a few projects. We will definitely make few open source projects.
Thanks, Santosh. Questions are starting to come in thick and fast now. What is data leakage?
Data leakage is when you, it's hard to explain really. So typically in machine learning, you try and train your model and then you test it on independent data. But there are many ways that you could put information from the training phase side into the test phase side, and that's known as data leakage. It can lead to sort of falsifying high-level prediction.
Yeah, that's correct. And I want to just give a quickest example of data leakage. For example, if you have done the training your model and you are testing your model on the same data, that is the biggest example of the data leakage, because you are exposing your model already the data which you already trained, and you are testing on the same data. So probably you will get highest performance.
Thanks, Santosh. The next question is, do you work on local machines or use cloud resources to scale?
At the moment, we are working on local ones because we are not deploying our model anywhere. So in future, we have a few projects where we might deploy our models and then we will move to the cloud.
Thank you. Andrew McCann's put a note in about joining up to compare notes on some work that he's doing around predicting admission. So I'll make sure we pass that email address on to you, Joe. So I think the next question we'll pick up is, and this is really interesting, when shouldn't you use machine learning? What sort of problems does it not solve, or should you make a decision not to use it?
Sure, I can answer that. So, well, one is if clinical judgment is preferred. Two is that it really depends on the quality of your data. So if your data is insufficient, or if you don't have enough information about the key variables of interest, then machine learning won't be any good. There are there are other approaches available. So, for example, you might do causal inference instead of machine learning if you were trying to understand the real causes, or Monte Carlo, or yeah, I think that answers it.
Yeah, my goes to, like, you should not use the machine learning if you don't know the interpretability of model, especially in the healthcare. For example, if you have built some model for predicting the heart failure and you have like no explanation how your model is going to reach that decision, and you are completely like treating that model as a black box, then I should suggest you should not use that model until unless you are not able to explain how your model is reached to that particular decision.
And I think that leads quite nicely into the last question we've got, which says you spoke about deployment, but when you're developing your model, do you give much thought to how the models can be integrated into the actual clinical workflows?
I think for that we have a special team within HU, that is Health Economic Unit, which they evaluate like how the economical value will be for the model and how it's gonna behave. But definitely in the machine learning perspective, when we are trying to build any model or any problem, we always take care about the ethics of machine learning. So the model should treat it, should consider the inequalities of data or the patients, and also like the other parts to make sure. So our focus is not just to get the better performance in terms of accuracy or AUC. We also look into the other factor, how we're gonna explain like those outcomes in terms of the variable importance and the other factors too.
And the final question that we've got time for before we wrap up, which again kind of leads on from the last one. Is there a risk that machine learning will entrench health inequalities because you're building it from a training data set that has health inequalities already embedded in it?
Yeah, as I said, we always test this. So I think there's always problem is the biasness. So the bias is something like, as a human, we can introduce to the model. So there are many possible ways like bias can come into the model. For example, as a human, as I said, for example, if we have our own biases, then it's much possible, like, because I am writing the code, I can simply introduce those biases into the model. Sometimes the data itself have the biases, sometimes the model itself has the biases. So we consider all the aspect before building those kind of model or deploying those kind of models.
So thank you both so much. We're out of time. I think that was a fantastic session. Loads of really great questions there. We have got some more training coming round on machine learning, so do go and have a quick look on the website to see which courses we've got coming around to find out more about machine learning as we go. Just before we wrap up, massive thanks to Joe and Santosh, but just a little prompt. Andrew Barraclough has just popped a note into the chat about the testing that AFRA are running on the National Competency Frameworks for analysts. So it's all about the professionalisation of our workforce. It's a really important agenda. Do go and have a look. We're working on the speakers for the huddle in a couple of weeks' time. I think it will be a joint effort from NHSEI and the Office for Health Improvement and Disparities, showcasing a couple of pieces of work that the teams there have been working on recently. It's 11:59, so massive thanks for joining us, and see you in a couple of weeks' time.